Okay, in this set of video notes, we're going to be covering Chapter 10 from our textbook. The subject, obviously, is gases. So basically, a gas, I'm sure you guys are pretty familiar with its own state of matter, so very different from liquids and solids in that they can expand to fill their containers like liquids do, but they're highly compressible, which liquids and solids are not, and they have very, very low densities. One thing to be careful of when we're talking about gases is that water vapor is not a gas. Vapors are a substance that are basically the gaseous state of that liquid, so it's a little bit different. Gases are a gaseous state under normal conditions, so like oxygen gas, for example, or helium gas, something like that. When we talk about gases, a lot of times we're going to be talking about pressure, and pressure is just the force over a unit of area, so pressure is force over area. Atmospheric pressure is the weight of all the air of the atmosphere per unit of area. So for example, we often talk about like 14.7 psi here in the United States, pounds per square inch. So 1 square inch of atmosphere weighs 14.7 pounds. Some of the other units of pressure that you might see is a Pascal, which is 1 Newton per meter squared, or a bar, which is 10 to the 5th pascals, or 100 kilopascals. We don't see those as often, though. How do we come to these measurements? What do they mean? The more common units we do see are millimeters of mercury, or torr. So like if you were to look at any barometer in the United States, you would probably see millimeters of mercury. And these are really literally come from when we first figured out air pressure, and it's literally the difference in heights of two connected columns of mercury. So if you were to take this tube in a vacuum and submerge it in the mercury, the air pressure, the weight of the atmosphere would push down in the mercury, and then that would push up the mercury into the column. So that height is literally the millimeters that it pushes it up. So the standard unit is atmosphere. So 1 atmosphere is 760 torr. So that's a conversion you'll be very familiar with. One way that we can measure the differences between the pressure of a gas versus the atmospheric pressure is this instrument called a manometer. So in this case, instead of being hooked up to that pool of mercury, you're hooked up to some kind of cylinder or whatever with a gas in it. It's open, sometimes closed, to if you're trying to get atmospheric pressure, it's going to be open here, and so that you can basically figure out, if you know what the atmospheric pressure is, you can figure out how much pressure this is exerting to push that mercury back. And so then the pressure of the gas is just the atmospheric pressure plus this height right here, which you can easily calculate. So again, standard pressure is just normal atmospheric pressure at sea level. So that's standard pressure. 1 atmosphere, 760 torr, which is 760 millimeters of mercury, or 101.325 kilopascals, which you'll probably almost never see. Pretty much everything is going to be in atmospheres or torr, and you might have to convert to atmospheres. So some gas laws that you may or may not have heard of. Boyle's law: the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. So if you look at this guy right here, we're open to the atmosphere, and there's 60 milliliters of gas compressed in there. If we add more pressure, whole another atmosphere of pressure, it's pushing down even more, or adding more mercury, it's pushing down even more, so that gas is compressed. Right? Scuba divers use this a lot. Right? If you take a breath of scuba air at depth, let's say, if you were to hold your breath as you rose up, that would be really bad, right? Because the water pressure would be decreasing, and as that would happen, the volume of your lungs would expand, and obviously that would not be good. So, for example, I am scuba certified, and my scuba instructor basically said that they always want to see, if you don't have your regulator in your mouth, a stream of bubbles coming out of your mouth, so that you're constantly have this, like, basically you have an open passage so that gas is not being trapped in your lungs, that you're allowing it to escape as you ascend to the surface, so that doesn't happen, because basically you could rupture your lungs. Yeah, fun, huh? So again, inversely proportional. So if you were to do a plot of just pressure and volume, you get a curved line, pressure versus volume. But if you did volume versus 1 over pressure, you're going to get a straight line. So meaning they're inversely proportional. Charles' law is kind of similar to Boyle's law. This says that a volume of fixed gas at constant pressure is directly proportional to its absolute temperature. So as it warms up, it expands, right? And as it cools down, it contracts. And so if you take the same balloon, if you heat it up, it would expand. If you cooled off, it would contract. And very similarly, this is volume versus time. Since they're directly proportional, is going to give you a straight line. Avogadro's law basically says the volume of gas, again at constant pressure and temperature, is proportional to the number of moles of gas in there. So that makes sense, right? And so you see that 1 atmosphere, constant temperature, we have 1 mole of gases. Doesn't matter what the gas is, it's going to take up 22.4 liters. So even like a CH4, which would be relatively much larger than helium, still 22.4. Those 6.02 times 10 to the 23rd moles, or 6 molecules, which is 1 mole of gases. So, so far we've seen that volume is inversely proportional to pressure, directly proportional to temperature, and directly proportional to number of moles. So if we're to combine this, volume we have is proportional to number of moles times temperature over pressure, in that the constant of proportionality, known as R, is the gas constant. So there's a lot of different values. Mostly we will be using liter atmospheres per mole Kelvin, so 0.08206. So if you put that in, now we've got volume equals our proportionality constant times NT over P, rearranged a little bit to be a little convenient, is PV equals nRT, or PivNert sometimes. So this is your ideal gas equation. Pressure times volume equals the number of moles times your gas constant times temperature. And temperature, by the way, is always going to be in degrees Kelvin. You can also figure out the density of gas using this equation. So if you divide both sides of our ideal gas equation by V and RT, this is what you get. All right, this is pretty basic. And we know that moles times the molecular mass equals the mass of whatever it is that you're trying to measure. So N times big M for molecular mass equals little m, which is the mass. So if we multiply both sides by the molecular mass, we get little m, so mass over volume equals pressure times the molecular mass over the constant times temperature. And that basically means, well, since we know that mass and volume equals density, now we know we can figure out the density of a gas. So rearrange that a little bit again. If you got density equals P times M over RT. Or you can figure out the molecular mass. The molecular mass is just the density times the gas constant temperature divided by pressure. So we can rearrange that a couple different ways to be a little bit more useful. Another law that we will take advantage of is Dalton's law of partial pressures. And this is pretty easy. Basically, that the total pressure of a mixture equals the sum of the pressures of all the other gases. So basically, the total pressure is just the pressure of the partial pressure of whatever gases. If there's 3, 4, 5, 6, 7, they all have their own pressure that they exert, and they're independent of each other. So if you collect a volume of gas over water, there's going to be water vapor mixed in with that gas. So if you want to find just the pressure of the desired gas, you can subtract the vapor pressure of the water. We'll also talk about mole fractions in your gases. So basically it's the ratio of the moles of a gas component to the total moles of a gas mixture. And that relates to the partial pressure. Right? So the partial pressure is related to the number of moles of a gas mixture. So if you increase the number of moles, you're going to increase that gas's pressure, or its partial pressure, which makes sense, right? The kinetic molecular theory explains, this model of understanding what's going on with the different molecules, explains a lot of what we see going on in gases. But there's a couple different assumptions that are made by the kinetic molecular theory. First is that gases consist of large number of molecules that are in continuous random motion, right? So we know that all molecules are always in continuous random motion, and then if you're talking about a gas, there's going to be a lot of gas in there. The combined volume, though, of all that gas, even though there's a lot, they're very, very small molecules. The combined volume is basically negligible compared to the volume of the container. There are a lot of molecules, but they're pretty spread out. So we assume that there's really no attractive or repulsive forces between the gas molecules, or if there are, it's very negligible. This one is important. Energy can be transferred between molecules, so as one's moving along quickly and it smacks into another molecule, obviously it's going to slow down, but it's going to speed up the one that it just ran into. But overall, this is important here, the average kinetic energy does not change with time, as long, this is important here, as long as temperature in the gas remains constant. So the average kinetic energy of a gas is not going to change, and you'll see that popping up later. However, the average kinetic energy is proportional to the temperature. So if we increase the temperature, we are going to increase that kinetic energy. So what does this mean for us? So KMT, Kinetic Molecular Theory, accounts for lots of different things. One, the compressibility of gases. So because there's large distances between these molecules, we said that the volume is of the gases is very small compared to the container, so that explains why you could compress a gas. It also explains Boyle's law. As you decrease the volume of a container, you're going to be increasing the number of collisions that molecules have with the sides of the container, which is going to increase the amount of pressure being exerted upon that container. It also explains Charles' law. As you increase the temperature, you're going to increase the kinetic energy, which is going to increase your collisions, which is going to increase your pressure in the vessel. Avogadro's law, right? Just like we saw, the same pressure and temperature, equal volumes of gases contain equal numbers of molecules, so 1 mole is always going to occupy 22.4 liters at standard temperature and pressure. That's what that means, standard temperature and pressure, STP. And then Dalton's law of partial pressures, these molecules are not really interacting with each other. They're not attracting or repelling each other. So this means that the pressure of one gas is going to be unaffected by the pressure of another gas because they're not really attracted to each other or repelling each other. So this leads to a couple other cool gas phenomena that we'll talk about. Effusion is the escape of a gas molecule through a tiny hole into an evacuated space. Okay, so you see this all the time if you get like balloons for your birthday and eventually those helium balloons kind of stop floating. That's because the helium has effused out through the tiny pores in that balloon. And this is the important thing, the rate of effusion is based on the molecular mass of that gas. So a lighter gas is going to effuse much faster than a heavier gas. But again, they all have the same, at the same temperature, they all have the same average kinetic energy. They're just going to diffuse faster. They're going to fit through the holes better. Diffusion, very similar. It's just the spread of one substance throughout a space, throughout a second substance. And again, that's going to be related to the mass. So a smaller thing is going to diffuse faster than a larger one. So finally, in the real world, we would talk about the ideal gas law, right? In the real world, things don't really work according to the ideal gas laws all the time. So it's only going to conform to the ideal gas equations at relatively high temperatures or relatively low pressures. So we're down here, right? Low pressure and relatively high temperature, low pressure. So this is where we're behaving ideally. Even the same gas will show wildly different pressures, different behaviors under higher pressures and at different temperatures. So it definitely breaks down when you're not at our ideal conditions. So why is that? Well, basically because when you're at higher pressures or lower temperatures, the assumptions of our KMT model start to break down. Right? We said there's a negligible volume of gas molecules and there's no attractive forces, but that doesn't really work as well. They're a lot closer than the intermolecular forces that we said were negligible now are no longer negligible, so they're going to start to affect things. And the same thing, if your temperature is really, really low, then they're going to be moving a lot more slowly, and so again, those IMFs that we could have, those intermolecular forces that we could have ignored before, we can no longer ignore. So you see that at really high pressure and really low temperature, it's going to start deviating from your ideal behavior. And that is that. We'll go over this a little bit more in class.